Good morning and welcome. So today we will start image classification. There is some part left in the structure from motion part, but we will start this because time is running out because this section is important. So today we will look at the basics of classification. I know that you have taken a course on deep learning, and then we will move on to convolutional neural networks that are good for image classification and so on. Uh, yes. So as usual, you are most welcome to ask any question through the chat or turning on your microphone. Yes. So if you take a brief history, in 1950s, neural net, so the so-called the perceptron, invented by Rosenblatt, came into being, and then the neural nets popularized and then abandoned as being interesting but impossible to optimize and unprincipled in 90s. But for example, Professor Jan LeCun and others achieved state-of-the-art performance on character recognition with convolution neural networks. At that time, he was at uh, New York University. Now he's the chief scientist at Facebook also. So some of my students have met him, very happy about it. And then in 2000s, Professor Jeffrey Hinton, these people kept on working. You know that finally Professor Hinton won the Nobel Prize. Uh, This era was substantial progress in some areas, but computer vision community ignored these researchers. So some researchers got angry about this. But finally, in 2012, due to this AlexNet paper at ECCV 2012, ImageNet Challenge, everyone started noticing this. AlexNet is one of the most cited papers in the most cited in the world. Okay, so let's look at image classification. Now you can see there is an image of a dog. So this image has that many pixels. So what we want to do is as the output, pick one of these classes that can be. So there are several classes: cat, dog, deer, bird, car, truck, and so on. And we want to pick one of them. But actually what the computer sees is something like this. It's just a set of numbers. Yes. So there is this big semantic gap between what the computer sees, the set of numbers, and what we want to get out to call it a dog. So for the computer, an image is just a big grid of numbers. So for example, 800 by 600 times 3 for three channels. We have seen this when we started this course. So what are the challenges in this? So many challenges are there. One is viewpoint variations. For example, you can see the same dog can appear in entirely different viewpoints. And then due to this, this set of numbers will drastically change. Yeah. So then intra-class variations. So there can be different dogs and they look different in size, shape, color, and so on, right? Then fine-grained categories are there. So we know that this is, I think, a beagle, and there are Dachshunds, um, German Shepherds, like the Labradors, like that. There are different breeds of dogs. So fine-grained categories. And then there is background clutter. You can see a lot of background clutter, for example, here. It's very difficult to identify the dogs. And then illumination changes are there. So here you can see some illumination changes, deformations are there, then occlusions. So here you can see the grids are occluding the dogs, and some of them cannot even be identified by a human being. Yes. So these are the challenges. So this image classification, that means giving a class name to an image. We take an image and we call it a dog. We take an image, call it an airplane. We take an image, call it a ship. This is actually uh, classification is so important even for object detection. So when you think about object detection, we want to not only give a class name to a window, we want to draw that bounding box. For in each image, there can be more than one bounding box, and for each of these bounding boxes, we give a class name. This one is called object detection. And sometimes we want to write something about the image. Okay, there is a horse and there is a rider, and it is the horse is stepping into the sea and so on. So this is called image captioning. For all these tasks, the classification is extremely important. Okay. So now let's look at the machine learning approach for the classification. So unlike example, sorting a list of numbers, there is no obvious way to hard code an algorithm for recognizing a cat or some other classes. We must go for a machine learning data-driven approach. What is the reason? Because we cannot write set of rules because there are too many pixels. Because there are too many pixels, handcrafted rule writing is impossible in these cases. So what we usually do is we collect a data set of images and labels. That means, for example, here you can see these are the automobile images. And we have a label for that, right? Label data set. And then you use a machine learning train the classifier. So you give images and labels. So two types of information are given, the images and their labels. And we do training and then we have a trained model. Yes. So then once we have the trained model, what we do is we take the test image and the trained model, and then we do this task of prediction. And then finally, we will have a predicted label. So this is the process of the machine learning approach for image classification. Okay. So let's briefly look at the data sets that are available for this. So one of the early data sets is MNIST. There are 10 classes, digits from 0 to 9. You can see some of these images, 0, 8, 3, 1. All these are handwritten. So 50,000 training examples. So that means each digit will have 5,000 images and 10,000 test images. So we train the classifier on training images and we test the classifier on test images. So to test each of the digits, we have 1,000 images each. So therefore, for 0 to 9, 10 digits, there are 10,000 test images. So thing is, the results from MNIST do not often hold on complex data sets. There are larger and larger data sets. So they need specialized classifiers. But this is one of the early experiments that people did. We also worked on this data set some time ago. So yeah. Okay. So now next we have the so-called CIFAR 10 data set. This one. There are 10 classes. So you can see airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And 50,000 training images, 5,000 per class, 10,000 testing images, 1,000 per class. And these are 32 by 32 RGB images. So therefore, each image will have 32 times 32 times 3 numbers, right? I think that is 3,072 numbers are there in each image. Then we have CIFAR 100. That also is a similar one, but there are 100 classes. 100 classes, 50,000 training images, so 500 per class, 10,000 testing images, so 100 per class, exactly the same size images. And then there are 20 superclasses also, 5 classes each. For example, if you take aquatic mammals, beaver, dolphin, otter, seal, whale, 1, 2, 3, 4, 5. These five classes are in this superclass. Trees, maple, oak, palm, pine, willow, these are in this trees class, and so on. So you can see the format of the CIFAR 100 dataset. Then there came the ImageNet dataset. This dataset was actually the first author is Deng, but Fei Fei Li, it's attributed to Fei Fei Li on Stanford University. So they collected millions of images. So about 1,000, there are 1,000 classes in this, about 1.3 million training images, about 1,300 per class, and 50,000 validation images, about 50 per class. 100,000 test images, 100 per class. Test labels are secret. So what is the difference between the training set, validation set, and the test set? We train the classifier on the training set and we validate that to fine-tune the hyperparameters. We will look at some hyperparameters today, hyperparameters on the validation set, and then the test set is actually hidden. So images are usually of variable sizes in this ImageNet dataset, but usually people resize them to 256 by 256. There is also a 22,000 category version of ImageNet, but less commonly used. This is one of the greatest contributions to computer vision. Actually, Fei Li gives a talk also, TED talk also in that. It's instructive to watch that TED talk. This MIT places, it is a scene classification data set. There's 365 classes of different scene types, scene classification, and 8 million training images, 18,000 validation images, 325,000 test images. Images have variable size, often resized to 256 by 256. You can see miniature, rainforest, field road, like that. Different kinds of scenes are there. Then there's another one called Omniglot. This Omniglot dataset has 1,623 categories, characters from 50 different alphabets. So these are different alphabets, different languages. 20 images per category, made for testing few-shot learning. So whether you can learn a classify or modify a classifier using a few images of that. That is the purpose of this one, Omniglot. Okay. So let's first, okay, now data sets, we looked at the data sets. We understood what a classifier is. Now we looked at some data sets. Now we look at one of the very simple classifiers called the nearest neighbor classifier. I think you all must have studied about this nearest neighbor classifier. So the thing about this nearest neighbor classifier is it memorizes uh, all the data and labels, predict the label of the most similar training image. It's very simple, right? Most similar training image. Now, if you think about an example, this is like this. Think about an airport. People are clustered in an airport. So you ask one person, from where are you? He will say, I'm from Sri Lanka. Then if a person is close by to him, you could think that that person is also from Sri Lanka. So another person is, let's say, from UK, and person sitting close to him, we call him UK. So nearest neighbor. So but you can see, for nearest neighbor, we need the labeled data, and also we need some distance metric. How do you measure the distance between two neighbors? Okay, some questions. So these are important questions. They are in the quiz also. With n examples, how fast is training? There's no time required for training. It's constant time. We call it O1, constant time. It does not depend on n. N examples are there. So here you can see these are the examples. Here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 examples. So what my task is, if I give a new dot and I want to find out whether it's a blue dot, a green dot, or a orange dot, I just need to see the distance. So there is no training phase that is required. So it's constant time. With n examples, how fast is testing? So in your testing, that means when you want to see what class this cross belongs to, you have to test with every single possible dot available in this, right? You have to find the distance between the cross and every single possible dot in this uh, data set. So that's why it takes n computations. N distance computations are required. Obviously, you can understand this. This is bad because we can afford slow training, but we need fast testing, right? Testing time, consuming time is not good. So there are many methods for fast approximate nearest neighbor. So there are fast ones, but the simple one is slow. Okay. So I have shown you a brief example uh, of what that would look like. So we find the distance to all the neighbors, all of them, okay, all of them. I have not drawn all arrows, but you have to draw all 10 arrows and then find the closest one. Obviously, you can see this one is the closest, so we assign blue as the class of that one. Yes, is that clear? Any questions about the nearest neighbor classifier? Very simple. So now, one thing that we need to understand is this one is in the two-dimensional space. But if you take, for example, CFA 10, we said that an image is 3072 dimensional. So therefore, your space will not be 2D, but not 3D, but not 4D, but 3072 dimensional. You cannot even imagine the dimensionality of this. So within that, you have to find the distances. Yeah. Okay. So here are some nearest neighbors shown. If you take the ship, this ship, so nearest neighbors, most of them are wrong, right? Yeah, for this one, it's generally okay. You give this and we find the nearest neighbors, uh, nearest 10 neighbors in the data set. You can see some of them are wrong, some of them are correct, right? So that's all. So you can see this one is correct, this one is wrong, this is correct, nearest neighbor is correct, this is wrong, correct, wrong, wrong. Oh, okay, I have done red and green. This is correct, this is correct, this is correct, and this is wrong. The nearest neighbor. So these are nearest neighbor, this is second nearest neighbor, third nearest neighbor, fourth nearest neighbor, and so on. I hope this diagram is clear to you. Okay, so how do we do this? So now let's see, it's a very simple metric, so-called the L1 distance. So I said we need a distance metric to get the nearest neighbor running. So this one is called the L1 distance. It's very easy to compute. You get the individual differences between coordinates and sum them. X difference, Y difference, and so on, so on. Okay. Get the differences and sum. Uh, so you can see 56. Now consider this as a test image. Consider this as a training image. Okay. So 56 minus 10 is 46. And so on, right? We subtract corresponding pixels. And then we have this and we sum them. 456. See, there's the summation. 456 is the distance between this. So now we have a distance metric, so-called L1 distance. And then using that distance metric, we can find the nearest neighbor. So this is a pixel-wise distance. Actually, this distance is wrong. The reason is because when you take an image and it slightly changes its position, slightly translates, then all these distances become wrong, right? Due to a slight change. So this is one big problem in using pixel values to represent images. Okay. So in this diagram, I show the so-called nearest neighbor, k equals 1. So based on one nearest neighbor, you make a decision. So for example, you can see these are the three classes, the blue class, the orange class, and the green class. So in this area, it is blue. The reason is mostly it's blue. But if you take this one, there is an orange one there, right? So for around that, there will be the orange class. Because whenever something we want to check one of those positions, the orange one will be the closest neighbor, not the blue ones. Actually, we want the blue ones to be the closest. We know as human beings that region belongs to blue. But because of this k equals 1, one nearest neighbor thing, it becomes an orange one. I hope that idea is clear. Then we have, I have drawn k equals 3. In k equals 3, you can see we consider 3 nearest neighbors. So therefore, in this region, you can still see blue, not orange. The reason is that when you consider 3 nearest neighbors, 2 of them will be blue, not orange. So therefore, this orange one cannot affect that. Yeah, I hope you can understand that. So this noisy orange one is not affecting the decision to be green at each of those points. where we can provide a test example. I hope this is clear to you. If nothing is clear, please don't hesitate to ask me. So then I have drawn k equals 5 also, and then k equals 7. What happens? When we increase the number of neighbors that we consider for the decision, the boundaries become smooth and smoother. But there will be some training error. That means during some errors are made for the training examples. You can see here, there's an error. This is this training example is getting classified as blue, but it is actually orange. But smoothness is there. So therefore, whenever we place a test example here, across we place here, it will be properly classified as a blue one. Okay. All right. Uh, then we have a mechanisms of finding distance also. As the first one, we saw the L1 distance, but there are other distances that can be used. Here are some of those distances. Minkowski discusses dxy, distance between an image x and image y, is taking their pixel differences, raising to the power of p and getting the 1 over p root. So when p is equal to 1, you have the L1 distance. So we call it Manhattan distance, L1, p is equal to 1. So distance for the two-dimensional case grows like that. You can look at this diagram and think about it. And for the L equals 1, P equals 1 case, the distance metric is this one. Then you have the famous Euclidean distance. We call it L2 or P equals 2 in this one. Then you can see x I minus y squared because it is Euclidean and you have to get the square root of the whole thing. The distance grows as circles in this case. So I have shown two examples of k equals 1 and k equals 3, p equals 2 and p equals 1. So I think I use k equals 3 here also, I think. So you can see the when p is equal to 2, that means Euclidean distance, you can see the boundaries can be slanting. But here boundaries are sort of vertical, that kind of thing happens. This blocky nature is there when p is equal to 1. Okay, we'll move. So this is called k nearest neighbors, 1 nearest neighbor to k nearest neighbors. What are the hyperparameters? That means parameters, not data. What are the parameters that characterize the algorithm? What is the best value of k to use? What is the best distance metric to use? There are examples of these are the examples of hyperparameters. Choice of about our learning algorithm that we don't learn from the training data. Instead, we set them at the start of the learning process. That is what the hyperparameter means. With the right choice of distance metric, we can apply k nearest neighbor to any type of data. K in the hyperparameters, we have the k as the hyperparameter there. Best value of k to use depends on the situation. But usually k equals 1 is not a good choice, but 3, 5, and so on, they are okay. Distance metric also, that depends on the situation, but you can use Euclidean distance. Okay. Any questions up to now? Please don't hesitate to ask. I also become happy when you ask a question. Don't we take the K from the graph like the elbow? Yeah. That's a good thing, good question. We can draw a graph and see what is the best value of K to use. That's true. There is a way to choose K, yes. Okay, so when you choose hyperparameters, we can choose hyperparameters that work based on the data. That means the training data. bad k equals 1 always works perfectly on training data. Training data will be perfectly classified if you use k equals 1. But this is not good because the generalization is gone. What that means is for testing data, it can make mistakes. You saw that in this diagram, for example. Now, in this one, the question is, uh, I can use a pen. Now, if the test example falls right here, you can see the little hand-like thing that right there, you will call it orange. But as human beings, we know that's not the orange region. That's the blue region. So all the training examples are perfectly classified, but the test examples are misclassified. This is what happens when k is equal to 1. So using the whole data set for hyperparameter choosing is wrong. Idea number 2, split the data into train set and test set. Choose hyperparameters that work on the test data. What's the problem with that? That's a bad idea. No idea how algorithm will perform on new data. So what is the right thing to do? This is the right thing to do. Split the data into train set, validation set, and the test set. And we choose K based on the performance on this validation set and test on the test set. But you don't keep on testing on the test set. Then as a human being, you will somehow make it tuned to the test set. This is not good. Also, people use so-called five-fold cross validation. What that means is split the data into folds. Try each fold as validation and average the results. So this is 5 folds. You can see fold 1, fold 2, fold 3, fold 4, and fold 5. We can evaluate the hyperparameters here and test on them. And so on. We can use different folds. But test set is separate. This is good for small datasets, but in deep learning, we frequently don't use this. Okay. So this is the graph that Sanju mentioned. Thank you. So for example, this is the cross-validation accuracy and this is K. So you can see sort of somewhere here, we have the highest accuracy, right? Somewhere here also. Highest accuracy. So about K equals 7 or so. You have that best highest accuracy. Yeah, thank you very much for that point. Okay. So there's a thing called K-nearest neighbors universal approximation. As the number of training examples goes to infinity, nearest neighbor can represent any function. What that means is this. Now this blue one is a true function. And we use one training point. If we have just one training point, only thing that we can do is we can do a straight line horizontal. That's the nearest neighbor function to that. So you can see it's not correct. But if we have training samples as in the second image here, 1, 2, 3, and so on. So these are the, for this point, for example, for point 3, for example, yes, this is the nearest neighbor, and we call that as the value. So you can see, for if you take this point exactly, that's the nearest neighbor. If you take this point, for example, this is the nearest neighbor. Like that, you can select a value. When you increase the number of training points, you can see the function becomes a little bit closer. Blue one and the green one become a little bit closer. But if you have hundreds of training points, the blue one and green one are almost on top of each other. This is the universal approximation. Okay. Okay, now let's talk about a concept called curse of dimensionality. This is especially important in image classification because images are large in the number of pixels. And this one is also called the curse of, this is called the curse of dimensionality. For uniform coverage of space, number of training points needs to grow exponentially with the dimension. Now let's take examples. Let's call dimension 1, only x-axis. 5 points are there, the blue points and the green points. The whole space is nicely represented, right? With blue and the green points. But if you take dimension equals 2, there are 5 squared per 25 points to represent the two-dimensional space generally equally. But if you make it three-dimensional, you will need 125 points to represent this space generally equally. So when the dimensions grow, the number of data points that you need grows exponentially. So number of possible 32 by 32 binary images is 2 to the power 32 by 32. That is 10 to the power of 308. So here nearest neighbors on row pixels is seldom used. It cannot be done. Very slow at this time. Distance metric on pixels are not informative. Nearest neighbor with convolutional nets though, they work well. We will look at that later. So you can see an example of what happens there. The original image, the boxed image, shifted image, tinted image. All three images have the same L2 distance to the one on the left. All of the same length, but you can see how different they are. So using pixels as features in this image classification is not a good thing. Okay. So to summarize this slide set, an image classification, in image classification, we start with a training set of images and labels and must predict the label on the test set. Image classification is challenging due to the semantic gap. We need invariance to occlusion, deformation, lighting, intra-class variations, and others. Image classification is a building block for other vision tasks. Uh, the k-nearest neighbor classifier predicts labels based on nearest training example, distance metric, and k are the distance metric and the k are the hyperparameters. I forgot a dot here. Distance metric and k are the hyperparameters. Choose hyperparameters using the validation set. Only run on the test set once at the very end. Decision boundaries can be noisy, affected by the outliers. Instead of copying labels from the nearest neighbor, take majority vote of k closest points. Using more neighbors helps smooth out rough decision boundaries, but they increase the computational complexity. Yes. So that's what I want to cover about the basics of classification. So we can take any questions if you have. Please do not hesitate to ask. Okay, let's start this lesson. Linear classifiers. I hope everyone is ready. This one is, you need to slightly concentrate on this. There are some things that you may not know here, uh, like the logistics, softmax loss and the SVM loss. Maybe you already know, but we will go through them. Okay, so I have the picture of the dog. I like that dog very much. It's a beagle. I think beagles have extremely good demeanor. That means they don't bite you and so on. They are very friendly dogs, beagles. But I'm not allowed to keep a dog. Uh, okay, so let's start now. So this is the input image. And this one is an array of 32 by 32 by 3 numbers. It's a 32 by 32 because of the color. We have three such planes. So therefore 3072 numbers are there. Okay. Then what we do is we feed that image to a so-called scoring function. This scoring function will give a score to this image. So this is, we call this our X image. So later on I will get rid of this vector notation, that is X. And this has weights or parameters, weights. So different people use different terms. So some people use theta for this. We use W. So it gives a score to the dog. So output 10 numbers giving class score. So it will give a cat score, dog score, deer score, bird score, car score, track score. So hopefully the dog score which should be the highest. Okay, now let's check the dimensionality of these things. X or the image. X is the image, right? X is the image. That's a 3072 dimensional vector. Therefore, to multiply that, we need 3072 second dimension of W, and first dimension W has 10 rows. And B is called the bias, and that one is a 10 number thing. It has 10 numbers. So finally, the output, the score, will have 10 numbers corresponding to the 10 classes. This is how we design this. I hope it is clear to you. Okay. Now let's take an example. Now take this image. It's a cat image. Cats are okay, uh, but they are not as friendly as dogs, as we all know. Assume that this cat can be represented using four numbers, okay, 2 by 2 numbers. It is large. It is larger than that. It's 32 by 32 by 3, for example. But let's consider that using four numbers, it can be represented. Somehow we decided to do that. 56, 231, 24, and 2. So we take these four numbers. Also assume that that um, in this problem, we have the uh, uh, cat class, dog class, and sheep class, for example. Each of these rows correspond to the weights of that class, correspond to the weights of that class, correspond to the weights of the sheep class. Yeah. So now how do you compute the cat score? You multiply 56 with this 0.2. This 0.2 multiplies this 56. This point minus 0.5 multiplies this 231. This 0.1 multiplies this 24. And this 2 multiplies this 2. And then you add this bias and you will get 96 minus 96.8. If you like, you can use a calculator and do it. I think these numbers are correct. Okay. So, but unfortunately, our cat score is low, but dog score is high. So therefore, this image is getting classified as a dog. What is the reason? Because we have not used any optimization to compute these weights and biases, but we must do that. That is actually the learning phase or the training phase. I hope that this example is very clear to you. So x plus b is the function that we apply, wx plus. So this one is w and this one is b. This is our x. And this is our fx. Fx comma w is this one. Very simple. Okay, that's the algebraic viewpoint. Okay. One thing that we can do is we can disregard the bias, but correct the bias vector, or put the bias vector also here, so that bias is added like this. It's very easy. Extra one, uh, to the data vector, bias is absorbed into the last column of the weights matrix. Yeah, that is possible. Okay. So now, what is the thing about this classifier? Let's look at this. Uh, we have fxw, w's for the time being, ignore the bias. Now let's, instead of x, let's put cx. That means let's multiply the image by, for example, zero point 0.5. So in this case, c is 0.5 and put that cx. Now what will happen? Because we have multiplied by zero point 0.5, this number will be get divided by half. This number will get divided by half. This number will also get divided by 2, not half, get multiplied by half. So this is the thing about the linearity of the classifier. Predictions are linear. So when we interpret this linear classifier in a different way, what we do is we take this row of numbers and rearrange it to the size of the image. Can you see that? We put 0.2 here, 0.5 here. Remember, this has the 4 numbers. Our image also has 4 numbers, 2 by 2, 2 by 2, 4 numbers. So we can arrange it to the size of the image. Now, and then the bias addition is there. Addition is there. So you can see, you take the image and multiply that by the dog template, sorry, cat template, multiply by the dog template, multiply by the sheep template, and get the cat score, get the dog score, and the sheep score. You can think about that way. So when you do that, these matrices will start looking like the corresponding class. It will look like a template of that corresponding class. So since we consider this as the cat score, this should look like the cat. Right now it doesn't, okay? So this will, if you do it for the all 3032, 72 dimension and optimize it and rearrange it like the image, you will see cat image like that. Uh, one thing is, now if you take the horse, for example, you will see a horse that looking this way and you will see a horse that is looking that way. What's the reason for that? Because in the data set, we had horses looking left and looking right, because horses are usually photographed like that. So these linear classifiers can have one template per category. A single template cannot capture multiple modes of the data. Okay, now let's look at the geometric point of view of this classifier. Now let's take the cat image. And in the cat image, let's take just one single pixel right here. Let's say 15 and 8 pixel. 8 here, 15 there. 8 comma 15 pixel. Okay, put a 0 also to say color. So take the value of that pixel. In that value maybe have 0 to 255 values, right? Right. And then we get the classifier score based on only that number. Based on only that number, we get the classifier score. So with just one number deciding that is not correct, but for the time being, let's see. So if this is the ship score blue one, cat score is the green one, car score is the orange one. So you can see in this region, ship score is the highest. So if this pixel value falls in that region, we call it a ship. Cat score is highest in this region. If the pixel value falls in that region, we call it a cat. In this region, car score is the highest. And this pixel value, if this falls in this region, we call it car. Okay. Uh, I hope it is clear to you. So whatever the highest score, ship score, car score, but he is just taking one pixel. Okay? There are so many pixels. Then after that, we have to take one more pixel. Let's say we take this pixel also. This is the pixel 580. This is the pixel 1110. So now you can see this is a line. So cat score increases this way. Okay? And not cat score, I'm sorry, this car score. Cat score is here. Car score increases this way. Car template on this line. So car score is 0 on this line. So like that, we can have a geometric point of view. So then the ship score and then the cat score and so on. Then actually in the two-dimensional space, you will see these kind of planes. So whatever the highest part in that region correspond to the cat region, car region, and the ship region. But here we are only considering two dimensions, but an image will have 3072 dimensions, for example. Then you can see this is a very high dimensional space. Within that space, these hyperplanes, whatever which is highest, that region where that hyperplane has the highest value will be the corresponding, will be the domain of that corresponding class. Okay, I hope it is clear to you. All right, but since these are linear classifiers, they make mistakes in cases like this. For example, if you take class 1, the blue one, and class 2 is the second and fourth quadrant, this is the first and so using a line, you cannot separate them. So cannot work with this. Class 1, the radius between 1 and 2. This radius is 2. That's class 1. And class 2 is everything else. So you can see you cannot separate this. And class 1, 3 modes. Everything else class 2. These circles. So using a line, you cannot separate them. So therefore, linear classifiers have these as hard cases for them. Okay. So now we saw the three points of view: algebraic point of view, the visual point of view, and the geometric point of view of a linear classifier. Any questions or comments? Are we okay? Okay. Now we move on to we have to slightly pay attention to this. I don't think this is difficult, but slightly pay attention to this. Yeah, I'll give you a minute or two. Okay. So now let's look at this example here. In this case, I have the 10 classes: airplane, automobile, bird, cat, and so on. So this is a cat image. This is the image one. This is a cat image. This is a ship image, image two. This is a airplane image, image three. So we can call it x1, x2, x3, right? So you can see in this one, this is the cat score. Is it the highest? Fortunately, it is the highest. In this one, this is the ship score, but this one is the highest. In this one, this is the airplane, this is the airplane score, but the highest one is this, right? So you can see if you don't have the classifier train, you will not get the highest score for the correct class. That's the score. Given a W, we can compute the class score for an image X. But how can we actually choose a good W? So what we do is use a loss function to quantify how good the value of W is. Find W that minimizes the loss function. This is optimization. Usually in our class, we use backpropagation or gradient descent for that. But for that, before that, we need the loss function. How to quantify whether a W is good or bad. Okay. Yeah. Forget about that slide. This is wrong. Okay. A loss function tells how good our current classifier is. If the loss is low, it's a good classifier. If the loss is high, a bad classifier. So this is also called the objective function, cost function, and so on. Sometimes a negative loss function is sometimes called the reward function, profit function, utility function, fitness function, and others. So given a data set, we have examples from 1 to n, that many images. Xi is the image, and yi is its label, integer label. It's an integer label, 1 to 10, or 0 to 9. Loss for the single example is Li is a loss. This is the scoring function, and this is the correct label. Loss for the dataset is the average of example losses. So we take all n examples, we sum them, and we divide by n with the average. Okay, now let's see two ways you can compute this loss. This is important. We want to interpret row classifier scores uh, as probabilities. This probability point of view is extremely important. We want to convert them to probabilities. So you can see classifier scores can be 100, minus 100, to 200, 1000, and so on. We want to take all of them and put them as a probability. What do we have to do? Probabilities are positive. We have to convert them to positive, and we have to normalize. That means add all of them and divide by that number so that the summation is 1. Making them positive and normalization are important. Okay, let's see how to do that. So let's take the score. This is the score function. S equals fxiw. I hope it's clear. Then the softmax function, p y equals k, belong class k, x is xi. What we do is we raise sk for that class score. Sk is that score, e to the power of that, divide by the summation of all these scores raised to e to the power. Now you know when you take a number and raise it to e to the power, it's a positive number. And you take all of them and sum and divide by that here, then you normalize it. So you can see in this case we have done the two things that I said are important, making them positive and normalizing. So this is also a differentiable approximation of the max function. So therefore, when we want to find the derivative or the gradient of that, it is possible to compute. So that's a softmax function. Then the loss for that example Li is negative log of that one. So this is the correct class's label. Negative log of the correct class probability. Okay, we can take examples. Now let's take this image. It's a cat image. So this is the correct class score. Correct class score. So you have to carefully watch this. Airplane score is 5.1. That is the highest. You know that this classifier is making a mistake now. You already know that. Ship score is minus 1.7. So these are unnormalized log probabilities or row scores. These are these numbers. These unnormalized, and they can have negative, they can have what, they can have any value. Row scores. We call them logits. Okay. Then we raise each one to the power of e to the power. So if you take your calculators and raise e to the power of 5.1, you'll get 164. I will just do it to sound sure. You have to say e to the power of 5.1 e to the power, right? 5.1. It will be 164.02. So you can see here, for high scores, e to the power will also give large values. For negative ones, e to the power will give very small numbers, but they all are positive. So converting to positive has happened due to this e to the power 0. All probabilities must be greater than those each. So this is done. But they are normalized because they don't sum to 1. But to sum to 1, we add all of them and we divide. So you can see this has 0.87, 0.13, and this is 0. So these are the probabilities. So when you take the probabilities, of course, you can see that it is calling it an airplane. That is wrong. What is the probability of the correct class? 0.13 is the probability of the correct class, 0.13. So therefore, when you want to compute the loss, we take yi, that's a correct class. So that is 0.13. Probability of the correct class is 0.13. So minus log 0.13. This is the loss that we are making. 2.04 is the loss for that cat example. It is high. But if you had some number large here, like 0.87, then this loss will be small. Because logarithm function, log function grows like that, right? Is that correct? Let's do that. So natural log function is like that, right? Because when it is less than 1, it is negative. So when it is close to 0.9, it's very close to 0. When it is like 0.1, for example, extremely large but negative. Extremely large but negative. Can you see? Extremely large but negative. And remember, there is a negative value in there. So therefore, those negative numbers will be converted to positive. So small numbers give large positive numbers. Large numbers close to 1 will give you small positive numbers. So you can see how the loss is happening. If it is correctly classified, loss is small. If it is incorrectly classified, loss is high. So this thing we want to minimize using some optimization scheme. This is how we can do train a classifier. This is called cross entropy loss. We call it multinomial logistics regression loss also. I hope this is clear for you. Any questions? Okay. So this is equivalent to maximal likelihood estimation. Choose ways to maximize the likelihood of observed data. I will not talk about it. Not ready for that. So actually, you can see the logic behind this also here. Now, these are the correct probabilities. That means the cat class probability must be 1, other probabilities must be 0, right? These are the correct ones. So you can compare these two probability mass functions using sometimes scale divergence and so on. So this is also fine. And then cross entropy, HP plus KLP, that is between P and Q. So these things are there in the slide. If you are keen, you can look at these interpretations. But I will not go through them in detail. Okay. So here are some questions. What is the minimum and maximum possible loss Li? What is the baseline loss before training? These are the questions. I'll give you a minute to think about it. What can be the minimum possible loss? Minimum possible loss happens when it is correctly classified, right? Model is assigns 1 to the correct class. When model assigns 1 to the correct class, this will be 1. Then the minimum value will be log of that, negative log of that. Yeah. Negative log of 1 is equal to 0. Remember the log function is like this. ln is 1, is 1.0. So therefore when it is 1, the value is 0. Maximum value, if the model assigns 0 to the correct class, then Li is log equals 0, log 0. So log 0 is minus infinity, and then you have minus sign there, so it's infinity. Yeah, thank you very much for the response. One person responded. There's a special case, uniform predictions. That means all classes get the same prediction, all classes. If the model is completely uncertain, predicts uniform distribution over C classes, that means Pj equals 1 over C for all the classes. So J equals cat, J equals car, dog, all these 1 over C. Number of classes is 10. So 1 over 10 or something. So loss will be minus log 1 over C. Because for the correct class, loss will probability is 1 over C. For all the classes, 1 over C. So this is log C. So for C equals 10, it will be log 10, 2.3. For a 10 class problem, so cross entropy loss will be 2.3. So it is well defined. For 100 class, you can see how much is that. ln 100. Okay. Okay, then we have multi-class SVM loss. I will give you some time to think about this before I move forward. I'll be back soon. Any questions about this? Okay. Then we can move to the next slide. So, okay, that's the softmax loss or the cross entropy loss. We cannot call it softmax loss, cross entropy loss. Then we look at the multi-class SVM loss. Okay. The score of the correct class should be higher than all other scores by a margin equals 1. That's the thing about the multi-class SVM loss. I will slowly explain this to you. Given an example xi, yi, xi is the image, yi is a label, score is fxw. Yeah, these are the scores. Then the SVM loss has the form max between 0 and this quantity. What is this quantity? For the time being, forget about this plus 1. Forget about this. And then this is the score of the correct class. Score of the correct class. This is the score of other classes. Score of other classes. Other classes. Okay. Now you can see we are subtracting from the score of other classes the score of correct class for what? For j not equal to the correct class. Only for the other classes, not for the correct class. We are subtracting. Okay. If the correct class's score is the highest, okay, assume that if the correct class's score is 5.1. These two are there only 3.2 and maybe 1 minus 1.7 or something. Okay. What will the summation result? Okay, 3.2 minus 5.1 is minus 1.9. Maximum value between 0 and minus 1.9 is 0. That's the first one. Then get the second one. Minus 1.7 minus 5.1 is minus 6.8. Maximum value between 0 and minus 6.8 is 0. So it's not making a loss. It is not making a loss. Okay. So now you can see how this formula works. Now let's consider this plus one also. Now, in this case, let's assume that this correct loss is 3.2. Okay. These incorrect losses, let's assume that they are 3.1 and minus 1.7 like before. Okay. Now take this for example. 3.1 minus 3.2, it's minus 0.1. But that is not okay because there is this plus 1. Minus 0.8 plus 1 is 0.9. You get 0.9 there. So you can see maximum value between 0 and 0.9 is 0.9. Let's take this one. Minus 1.7 minus 3.2 is minus 4.9. Minus 4.9 plus 1 is minus 3.9. Max value between 0 and minus 3.9 is 0. So now you can see in this case, the correct class has a higher score. That's good, but not high enough. It has to be higher by a margin of what? Higher by a margin of 1. Now you can see the value of this margin. So here this diagram shows that this is called hinge loss. Hinge loss means it's like a hinge. Saraneru, it's like a hinge. It's like a hinge like that. Yeah. So hinge loss. So this is the highest score among other classes. Highest score among other classes. For example, this 3.1. in this example. Margin, usually it is 1. Margin is 1. So this, the correct one's score must be 4.1 or higher. If it is greater than 4.1, no loss is made. Fine. Zero loss. If it is less than 4.1, you make this much of a loss. If it falls now, this is 0.9, it is falling here. So you are making a loss of this much. Can you see that? If it is falling here, loss of this much, and so on. So I hope you can see this, the value of this margin. This is the multi-class SVM loss. Any questions? Okay, let's move forward. All right, we can take examples. Remember, SVM loss is Li, J is not equal to Yi. That means the correct class label. Maximum 0, Sj minus Syi plus 1. So here we are saying, this one says loop over incorrect classes. Loop over incorrect classes. Okay. We'll take this first example. It is an airplane class. So correct class score is 4.9. Uh, Cat score is 1.3. Ship score is 2.0. You can already see the correct class score is much higher. Higher than 1.3 plus 1, higher than 2.0 plus 1. So therefore, it will not make a loss for this example. Let's see that. Maximum value between 0 and 1.3 minus, subtract the correct class. Yes, this is Sj, right? Syi, Syi. These are the Sjs, two Sjs. Yeah, plus 1. 2, this 2 minus 4.9 plus 1. So therefore, you will get 1.3 minus 4.9 minus 2.6, 2.0 minus 4.1 minus 1.9. So max value will be 0. Here also max value will be 0. 0 plus 0, 0. It does not make a loss. Why? Because the correct classes score is 1 above the highest score of all incorrect classes. Let's take the other example. Now, the correct class score is 3.2. So you put it here. Incorrect class losses are 5.1 and minus 1.7. So here you get 2.9. Here you get minus 3.9. 2.9 you get because there's this one margin also has to be added. So here you make a loss of 2.9. Here 0, altogether 2.9. Final for this one, you can see the correct classes loss is minus 3.1. It's making a massive loss. What's the final loss? You average all these three. 2.9 plus 0 plus 12.9 divided by 3, 5.29. So you can see how the SVM loss is computed. How it encourages the classifier to have a margin. Okay. All right. Now here are some questions. I will go through these questions and answers quickly, but you will have to spend time to think about this. So again, the loss is for that example, loop over other incorrect classes, maximum value 0 SJ minus yi plus 1. So we have the scores of the airplane cat ship and the loss we know at 0, 2.9 and 12.9. Question number 1. What happens if airplane score changes a little? So this 4.9 changes like 4.8, for example. Does anything happen? No, because this is much higher than the highest score. Much higher than the highest score. Nothing will happen. As the airplane loss 4.9 is much higher than the others, the loss will remain 0. Second question, what is these slides are from Justin Johnson. What is the minimum and maximum possible loss? Of course, minimum loss is zero. You can see all classes are correctly classified by a margin. Max loss is infinity when the score of the correct class is very low. So if the score is returning a large negative number, uh, then you can have that situation. Third question, if all the scores were random, what would we expect? Random is all the scores are random. That means these three numbers are sort of the same. These three numbers are sort of the same. These three numbers are sort of the same. So remember, in this case, you have to add over incorrect classes. Right? So in this case, the margin will be added twice. Margin is 1. 1 will be added twice. There are three classes, margin will be added twice. So here's the answer. Loss will be C minus 1. The loss will be C minus 1. C is the number of classes. That is actually 1 plus times C minus 1. 1 is a margin. That's how you get it. If there's anything not correct, please ask me. Then the last fourth one, what would happen if the sum were over all the classes, including I and I equals, not right, I equals yi. Including that, the summation we take even I equals yi also. This summation. Then above loss plus 1. Above loss plus 1 because this margin will be added. Uh, then question number 5, what is the loss used to use mean instead of the sum? So maybe here we are summing in mean. That means all the factors will be multiplied by 1 OC, no problem. Next question, question number 6. Weight, I don't know what happened. Weight matrices will change in a non-trivial way. If we use squared here rather than this one, square. So weight matrices will change in a non-trivial way, no longer be multi-class SVM loss. I'm not explaining this. I'm not ready for that also, so please think about this. Finally, suppose that we found some W with L equals 0. Is this unique? It is not unique because 2W will also give the same loss. Because these are linear classifiers, 2W will make the scores double, but still the loss will be 0 because all Sj and Syi will be increased. That means corresponding to the 0 loss, there will be multiple Ws. There will be multiple Ws. W, 2W, like that, there will multiple Ws are there. So therefore, we need to add regularity. What that means is we have to control W. Yes. Okay. So now if we compare cross entropy versus SVM loss, so you can see the cross entropy loss here and the SVM loss there. And we assume this scores and this is the correct class score. Yi equals 0, correct class score. What is the cross entropy loss? What is the SVM loss? So you can see this is 10 is higher than them. So obviously the SVM loss is going to be 0, but the cross entropy loss will be greater than 0 because it is the probability thing is working. What happens to each loss if we slightly change the scores of the last data point? Slightly changing, cross entropy loss will change. SVM loss will remain the same because it has this margin already greater than 1 or equal to 1. What happens if each loss is, if we double the score of the correct class from 10 to 20? cross entropy loss will decrease, SUM loss still is zero. So now you can see cross entropy loss is never satisfied. It will try to minimize the loss further and further by doing crazy things, but SUL loss can become zero. Okay. So now if we think about it again, so with the loss function, we quantify the preferences. We have some data set and we have some score function, and it takes the image W and bias, so we can call it WX plus B for linear classifier. We had the loss function for this is the multi-class SVM loss, this is the cross entropy loss. Now how do we find these W's and B's? So we have the W, we have XI, YI, labels and images. We give to this score function, it will produce a loss with the score and loss, and then that loss we have to minimize and change W and B. So minimize the loss and change W and B, which is a topic um, for another class. We have to look at gradient descent. But before we look at gradient descent, um, I want to look at neural networks. So after the break, we will look at neural networks. So we will meet in, we can take a break, meeting at 12:15 or so. So we'll take a break. So I'll pause the recording. Hello, welcome back. I hope everyone had something to drink or eat, and I also did. We can start the lecture on convolutional networks. So here we will try to study how convolutional neural networks are formed. Some of you may have already studied this, and then we will look at some historical networks and how to compute the number of parameters in those networks. Okay, so we looked at this paradigm where we thought about the linear classifier, and we realized that these rows of W can be seen as templates when we rearrange them. And we looked at the score function, and we looked at how to use the score function and to compute cross entropy loss or SVM loss. And then we said by using this loss, we run so-called gradient descent to find good W's and V. So even for a larger network where so many weight matrices are there, W's are there, we have the same paradigm. We have a score function, and we have to compute the better W's by using so-called gradient descent. So later on, we will see how to compute those gradients. To compute the gradients, we have to use the chain rule. And when you compute the chain rule, the gradients will have to be computed from the very end of the network. That means the gradients of the loss with respect to the parameters close to the loss. And we have to slowly propagate them back to the W's and B's that we want to compute. Update. So this is back propagation. We will look at that also later, but not today. Okay. Let's start with the so-called perceptron. This is the linear classifier, and we have x1 to xd. Well, he said that d can be, for example, 3072. This is the Rosenblatt's contribution, where you multiply x's with w's, and then you just get the sign. And if it is positive, it's one class. If it is negative, it's another class. So it's a linear classifier. Capturing d also into w, we can say f equals sine wx. So there you can see it's nonlinearity is there to decide which class it is, but we can use a scoring function, assuming k classes, not powerful in this case. So if you consider k classes, w is k times d. Then what people did was people added hidden layers um, to this. Then nonlinearity is always there. So in each of those nodes, there is a nonlinearity, for example, a sigmoid function. So if we add one more layer like so, I have given the sizes of this. Still, these two can be captured into W3. It is still a linear classifier. To have a powerful classifier, nonlinearity must be added to each of these nodes. If we add nonlinearities, we can learn a continuous boundary. That means not a line, but a curvy shape, segregating the two classes in 2D and then hypersurfaces in other dimensions. So examples of these nonlinear functions, some of you know, are the sigmoid function, hyperbolic tangent function, ReLU function. This is what AlexNet paper introduced. This one is the one that people usually use, Leak ReLU, and all the other things are there. So these are called multi-layer neural networks, so densely connected neural networks. So MLPs, people usually call them MLP, multi-layer perceptrons. So later we are going to look at how this optimum W can be found, but we will briefly talk about it now. So here you can see the loss this is the scoring function you can see subtracted from the correct class and then square it. So this is a squared loss function, and there's some regularizer term also to constrain W's. And then this is a function of W. So therefore, we should be able to compute the partial derivative of this loss L with respect to W. And if we can complete the partial derivative, we can do a gradient descent step. You can see this one is moving in the negative direction of the gradient. To compute the new W, this one is called gradient descent. So if we start Here, this is a 2W function, W1 and W2 only, but we know that many W's are there. Starting from there, you one step at a time, you move in the negative direction of the gradient. You can see it is climbing down the slope. This is called gradient descent. So we find the network weights to minimize the training error between true and estimated labels of the training example. Update the weights by the gradient descent. Backpropagation means gradients are computed in the direction from output to the input layers by combining using the chain rule. So we will look at this in detail later, hopefully. Stochastic gradient descent means compute the weights updates with respect to a small batch of examples. Some people call it mini batch gradient descent. At a time, cycle through the training examples in a random order in multiple epochs. This is called stochastic gradient descent. Okay. Uh, Given this, we have to once again remind ourselves in what happened in 2012. So in this ImageNet large-scale visual recognition challenge, ImageNet large-scale visual recognition challenge, in this competition, people were making so-called top five errors 28%, close to 25%. But suddenly there was this big improvement in 2012 with this AlexNet, and Jeffrey Hinton is the senior author of that, who won the Nobel Prize. Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton. I don't know what happened to Alex. I have not looked for that, but Ilya Sutskever, he started OpenAI also. And then these errors kept on reducing as years passed by. Okay, so let's look at what convolution is. So pictorially, I will show you what convolution means. Some of you may already know. So there is a kernel. You can see these are 3 by 3 matrix. We call it a kernel or a filter. All the numbers are 109s. So what we do is we keep this kernel on the image. This is the image. This is the center of that kernel. That's the center. We keep the center there. And with the numbers in the kernel, we multiply the underlying image pixel values. So in this position, all are zeros. So therefore, resulting value will be 0. Then what we do is we move the kernel to the next pixel. Now the center of the kernel is here. So you can see there is 190 over there. And this 90 will be multiplied by the value of the kernel, that is 109. You can see 109. So therefore, you get 10 here. Again to the next point. So there are two 90s overlapping with the kernel. So we get 20, 30, 30. And in a place like this, there are 1, 2, 3, 4, 5s. 590s. So you will get 50 and so on. So this is the output of the convolution operation with this kernel 1 over 9 times all ones. What is the thing about the border pixels? Can we get a value for this pixel? You cannot. The reason is if you keep the center here, the kernel will not fully overlap with the image. That's a problem. Kernel will not fully overlap with the image. So therefore, you cannot compute the value there. So that's why all these are borders. So here also you cannot. So there is a border of 1 for which you cannot calculate values. So people do different things to get values here. Sometimes people pad the image with zeros and do different things. Yeah. So in reality, the operation that we are carrying out is a correlation. This is the expression for that. Those who know about this discrete time convolution and so on will understand this. Otherwise, you can ignore that. Okay. So now this is a convolution one. Now let's look at the fully connected version first. Now, if this is an image, so there are so many pixels this way, so many pixels that way. To compute one number in this layer, that means let's consider, for example, this number. This number. To compute that, you can see the arrows are coming from all the pixels in the first layer. All the pixels in the first layer contribute to computing the value in this one, this value, this value. Yeah. To compute this value, for example, this node's value, all the pixels contribute. All of them, all are fully connected. They are fully connected. That's the meaning of that. Okay. But convolution is not like that. So let's look at the convolution now. So here is the image. Let's consider this as 32 height and 32 width and 32 height. And the depth is 3. That means it has RGB 3 channels. Okay. So this one needs, now this is our kernel. What you see here is the kernel. Its size is 3 times 5 times 5. 3 times 5 times. So spatial extent is 5 by 5. Height is 5 here. And this width is also 5. The depth is 3. Why? The image has 3 channels, or it's a color image. So to compute one cell in the output structure, you need 3 times 5 by 5 multiplications. Because in the image, in the window in the image, underneath this kernel, what you see right now, underneath this kernel, there are 3 times 5 numbers, so those have to be multiplied. So there are 3 times 5 multiplications. And additions also there. So that's that operation. Now, these numbers in the kernel are learned weights. They are learned through our backpropagation algorithm. So uh, running one kernel or one convolution filter gives a feature map. And you run multiple of them and get multiple feature maps or activation maps. So if you run 24 of them, you get 25 activation maps. We put them together. That's a feature map. So when you compute the next layers, one of the cells in the next layer, one of the values in the structure of the next layer, we take this as the full depth. Let's consider this as not 24 but 32. 32 is the depth of that. Okay, this can be a 5 by 5 convolution. Now you can see the computation complexity is higher. Number of computations is higher. So you have to have several that many filters to compute the next structure, next output activation map. Okay. Any questions about this? So please do ask questions if you have. Okay. Let's move forward then. Okay. Now let's see, when we have more than one image, what is the situation? Because we usually feed images in batches to these networks. So let's carefully see this. Now, one single image has 3 channels. Let's consider its height as 32 and the width as 32. And let's consider there are 6 filters. Let's consider the 6 filters first. And then let's consider multiple images. Okay. Then this is the kernel. So that kernel, let's call it as 5 by 5. And the depth of that kernel is 3. So 3 times 5 by 5 filter is what I'm showing here. And there's, of course, one single number called the bias. And then that produces a feature map over there. Then you run, okay, it will be 28 by 28 by 1. Why is the size reducing? because of the kernel not being able to fully overlap the image at the edges. We run one more kernel, then you get another feature map. We run one more kernel, you get another feature map. One more, another feature map. One more, another feature map. One more, another feature map. So in this example, I'm considering we are running 6 of them. So because we ran 6 kernels, you will get a feature map of depth 6. So this depth will be now 6. So the output activation map will be 28 times 28 times 6. 6 times 28 times 28 times. So 28 by 28 grid at each point, and each point, if you consider one point here, it will be a 6-dimensional vector here. So stack activation to get the 6 times 28 times 28 times sort of an image again. So when you run the next convolutional kernel, that convolutional kernel's depth should be 6 because of this. Okay. Now let's consider 4 images. Not only 3 by 32 by 32, of course, color images, but batch of 4 images. Each image is convolved with 6 filters. You can see the 6 filters here. So we have one image here, the first image. It will result in 6 feature maps. Okay, a question for you. If you complete this whole batch of images, whole batch of 4 images, what will be the size of the output feature map? What will be the size of the output feature map? So let's see whether we can answer. No answers, but that's okay. Actually, it is on the slide. It will be 4 of them, 4 of them. So 4 times 6 times 28 times 28, like that. For the second image, another 6. For the third image, another 6. For the fourth image, also another 6. I hope it is clear to you. Okay, now if you put in the notation, this is very important now. We have n batch of images. Each image has C in number of channels. It used to be 3 here. And the height of the image and the width of the image is there. So we have number of filters. Each filter size can be C in times KH times KW. We had 5 by 5 and 5 for this in the previous example. This used to be 3 because we had color image, and C out we decided, whatever, we decided it to be 6. So you can see here, due to each of these images, we get a feature map of C out's depth. So now you can see the batch output, the whole structure size will be this one, n times C out times H prime times W prime. What will be H prime W prime? Slightly less than H and W. Uh, Actually, we can compute that value. It will be H prime is H minus, let's say kernel size is KH plus 1. That will be size, right? So because we saw that if this is 32 by 32 and our kernel size is 5 by 5, 5 by 5 here, this will be 28 by 28. Okay. Yes. So now when you learn those filters, we saw that in the linear classifier, the filters could be interpreted as images, templates. And when they ran AlexNet, 11 by 11 weights, their filter size 11 by 11, they had two GPUs, the top, they call it top GPU and bottom GPU, two GPUs, the graphics processing units. They turned out to be sort of edges when they look at the templates. And in the bottom GPU, they turned out to be these color alternators, color patches, and so on. It's beautiful, right? These are things as human beings also we can interpret. Okay, now let's look at what a convolutional neural network should look like. We have an image. We run a filtering kernel and we get a feature map. We run another kernel, we get another feature map. Like so, we will run multiple feature maps. And then these feature maps are there. And to compute these feature maps, the convolutional kernels we learn. We learn through backpropagation, that comes later. And after that, we apply a nonlinearity, and then we do something called spatial fooling, and then we have the feature maps of the next structure. Nonlinearity is the ReLU nonlinearity. We briefly saw that. So it is very simple. If the value of that activation, that number, value of a, let's call it a pixel, value of pixel is greater than X, you take that value. If it is 3, you take 3, that's fine. It's no change. But if it is less than 0, if it is negative, you put 0. This is the very simple form of that very famous ReLU nonlinearity. Then spatial pooling thing is there. So you have a feature map, you want to reduce the size of that. What you do is you take 2 by 2 windows. In 2 by 2 windows, you pick the maximum value. We will look at it again. So like so, we get feature maps. So this sequence of operations continues. Image, conpool, 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 and then take all these numbers available here and densely connect it to the next layer, densely connect, and then finally you get a layer. So this is actually the structure of that famous 2012 network called the AlexNet. We will look at that in detail later. Okay. Okay, now let's look at that padding thing. So we saw that when you run a 3 by 3 filter, for example, the filter can be fully placed only here. This is the first location of the center where you cannot keep it here. You cannot keep it here. You cannot keep it here because then the filter will not overlap fully with the image. So therefore, no numbers here, 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 and so on. So for example, if you take an input 10 by 10 image, images are larger than that, but for time being, some images are missing. I will put that. I'm in a lecture. So these are That's the order. So if you take a 10 by 10 image, if the filter size is 3 by 3, you see you get an 8 by 8 image. The reason is input size is, let's say, WW, filter size is, let's say, K by K. So W minus K plus 1 will be the output size. So this is 10. Our K is 3. So here you will get 10 minus 3 plus 1. Okay. If you actually think about this further, if you take padding size P, output size will be, that means you pad the image with a series of zeros, for example, or whatever the number, then the output size will have this plus 2 POs. So P, you usually take the padding size K minus 1 divided by 2. So if it is a 3 by 3 filter, we take the padding as 3 minus 1 divided by 2 equals 1. So that is the padding size we should put. For a 5 by 5 filter, P has to be 2. For 7 by 7 filter, P has to be 3. Like that, we select the padding sizes. So P is equal to K minus 1 divided by 2. Output size is W minus K plus 1 plus 2P. This makes the output have the same size as the input. You pad like that. Okay. Uh, any questions about the padding? Okay, some people are asking for an image. I'll put that, otherwise you'll get confused. You say Sapphire image is not there, right? So I'll find it from somewhere. Should be there somewhere. That on the Moodle quickly. Sorry about that. Okay, now they're there. Sorry about that. Not having that. Okay, so the padding size is fine. So now let's look at the so-called resective size, that field. That means when you are going through layers up and up, if you take layer L, and take a thing here, it looks, if you take a layer L, this element here, if the kernel size is 3, would have resulted from the whole window here, right? 3 by 3, 1 gives rise to 1. So if you take the extreme cases here, this one and this one. In the previous layer, this will have resulted from a 3 by 3 window here, right? The next one, next corner one, this one from a 3 by 3 window here. So you can see the whole window resulting with that will be this 5 by 5 window. Then when you give one more, you can see you get a 7 by 7. So therefore, the rule is this: each successive convolution adds a k minus 1 to the receptive field size with L layers. The receptive field size will be 1 plus L times k minus 1. What that means is, if you have 1 to 3 layers, an element in layer L would have resulted from L plus k 1 plus L times k minus 1 window. So whole window's numbers would have given rise to that. That's the idea of that. The receptor field grows linearly with layers. You can see it is not L squared, it is just L linearly. So it's a downstamp. Okay. So then there's a thing called stride. Stride means this. When you're moving a window or a filter, by how many pixels do you move it? Do you move it by just 1 or 2? If you move it by 1, we call stride equals to 1. If you move by 2, we call stride equals to 2. So now you can see the stride is 2 now. Then again, the stride is 2 now. So now you can see because of those motions, we got a value here, we got a value there, we got a value there. That's all. Then we move by 2 pixels here, and we got a value here, 36. We got a value there, and so on. So now you can see, to compute the size of the output structure, the stride also will have to be considered. So 9 by 9 input, filter is 5 by 5, example 1 over 25. Stride is 2, output size will be 3 by 3. How do you compute that? If the input size is W, this is W, and the output size is what you want to compute, and the kernel size is K by K. So you will see W minus K plus 2P, P is the padding, you have to divide by stride, plus 1. That is how you compute the output structure size. So then there are the things called one-by-one convolutions. What they means is the spatial extent of the convolution kernel is going to be 5 by 5. We keep it as 1 by 1. Then it's called a one-by-one convolution. I hope that's clear. It is like stacking 1 by 1 convolution layers gives MAP operating on each input position, something like that. So okay, now let's compute the number of learnable parameters. For this, we'll take an example. This example. And these writings have come from a previous one. Okay. If an input image is of size 32 by 32 grayscale, and there are 6 filters of dimension 5 by 5, and if the stride is 1, padding is 2, compute. 1, output feature map size. 2, number of learnable parameters. 3, number of learnable parameters of, if the image were a color image, 4, number of multiply and add operations for the color image. So take a little time to think about this. Okay, here are the answers. So output size will be W minus K plus 2B divided by stride S plus 1. Padding is 2. So this is 2. Input size is 32. Kernel size is 5. So 32 minus 5 plus 4, that means 31 divided by 1 plus 1 is 32, 32. And there are 6 such filters. Output size will be 6 times 32 by 32, 6,144. Number of learnable parameters, second question. Now there are 6 filters. Each of the filters will have 5 times 5 kernels. Depth will be 1 because this is a grayscale image. And then 1 for the bias and 26 of them, each kernel. There are 6 such kernels. So therefore 26 times 6 is 156 learnable parameters. Question number 1, question number 2. Next question. The number of learnable parameters if the image were a color image. If it's a color image, this number becomes 3, right? So 3 times 5 by 5 plus 1, 76. So total will be 456. Okay. Finally, number of multiply-add operations. Each element in output needs 75 operations because 3 times 5 by 5 multiplications. Total multiply by add operation will be 75 times the output size. This is the output size. 6,144. So remember how you compute the output size. This example is an important example. Okay. Yes. So if you summarize these things that we discussed, so if the input size is seen, like for example, 3 h times w image, hyperparameters are width of the kernel and the height of the kernel, number of channels is C out, the number of kernels, padding is P, stride is S. So weight matrix will be C out times C in times KH times KW, giving out C out number of filters, on filters of size, C in times KH times KW. Output size will C out times H prime times W prime. H prime we can compute by H minus K plus 2P divided by S plus 1. W prime is W minus K plus 2P divided by S plus 1. So common settings are these. KH, KW small square filters. So P is K minus 1 divided by 2. To get the same padding, that means the input size of the image and the output size of the image will be same. So C in and C out we usually pick 32, 64, 120 to the powers of 2. So for example, K equals 3, P equals 1, S equals 1. So it's a 3 by 3 convolutions we take. K equals 5, P equals 2, S equals 1 for the 5 by 5 convolutions. K equals 1, P equals 0, S equals 1, this is 1 by 1 convolutions. If you want to downsample by a factor of 2, you can have S equals 2 and so on. Okay. All right. Then let's briefly look at max pooling. We already looked at it. It's very easy. So max pooling means you take a 2 by 2 window. and take the maximum value of that. So this is the maximum. See, for that we put 6 there. And then you move it by 2. The slide is 2 actually. And maximum value is 8. And 3 and 4. So you can see slide is 2. You move it by 2. Uh, Important thing is when if this 6 value, if it were here or here or here, there's no difference. You get the max value. So you can see the max pooling operator is agnostic or resilient to slight changes in the image pixels. If you pick slide equals 2, it downsamples by 2. There are no learnable parameters. So introduces invariance to small spatial shifts, no learnable parameters. Okay. Max pooling, if you look at the summary, input size C times H times W, kernel size K, slide is S, Pooling function can be max or average, output size C, H times H prime W prime, H prime can be H minus K divided by S plus 1, W minus K divided by S plus 1, learnable parameters null. Common setting, K equals to S equals to, K equals 3, X equals 2, Alex let use, but people don't use it. Okay. Now we are ready to look at the existing architectures. I'll give you some time if you have a question to ask. I'll be back in a minute. Drinking some tea. Let's look at the existing architectures. Look at some tea. Yeah. First, we'll start with the Lenet 5. This Lenet 5 was designed by Professor Jan LeCun when he was LeCun or LeCun, when he was at New York University. There they had to read the characters in checks, handwritten characters. So they have this MNIST dataset. We briefly look at the MNIST dataset today. It's handwritten with digits. So this neural network will give an output from 1 to 0 to 9, recognizing the digit. So little bit early network. So therefore some terminology is different, but I think we can diagnose that. So this is input image size is 32 by 32. And then they are saying that they run convolutions and the output size is 28 by 28 and 6 of them. So what that means is, what is the convolution kernel size? Because the size has reduced from 32 to 28, you know that this is a 5 by 5 convolution. 5 by 5 convolution. Mhm. So then he is doing subsampling and it resulted in 14 by 14 map. Of course, subsampling does not reduce the number of channels or the depth of the map. So there you can see he must have run 2 by 2 with stride 2, max pooling or average pooling by with stride 2, average pooling. Then again convolutions. So 14 has become 10. 14 has become 10 and there are 16 such maps. So this convolution must also be 5 by 5. Then subsampling again. So stride 2 subsample. That's why the feature map size has reduced from 10 by 10 to 5 by 5. So now let's compute the size of these feature maps. In this case, 6 times 28 by 28 is a size. Here 6 times 14 by 14. Here 16 times 10 by 10. Here 16 times 5 by 5. How many parameters are there? In this convolution operation here, how many parameters? So you can see the depth of this image is 1 times 5 by 5 convolutions. How many of them? 6 of them. And because of 6, there must be biases, 6 biases. So here you can write this as 25 times 6 is 156. 156 learnable parameters. No learnable parameters in the subsampling. I'll write the learnable parameters here, no, 0. Now in this convolution operation, 16 maps, 16 output maps times 5 by 5 kernels. But the depth of those kernels must be 6. The reason is in this map, there are 6 of them. Okay. So altogether, how much do you get there? 25 times 6 is 150. And of course, plus 16, right? To consider the bias. Yeah. This subsampling layer has zero learnable parameters. And then it's a fully connected one. What is the size of this structure? 16 times 5 by 5 is 400. So there's a connection from 400 to 120. The total number of weights will be, because it's a fully connected, but 400 times 120, and biases for each of the output nodes 120. Here 120 times 84 plus 8. Finally here 84 times 10 plus 10. This one is easy to calculate. That's equal to 850. Others also you can calculate and see how many learnable parameters are there throughout this network. If you wish, you can um, compute the number of multiplications also. I will not do that now. You can if you wish. Okay. Any questions about this? So if you want to compute the total number of learnable parameters, you have to add this, 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 and this. Do we have to learnable parameters for the full connection? Do we have to compute learnable parameters the fully connected ones? Yes. You have to compute the learnable parameters for the fully connected ones also. What does the Gaussian connections mean here at the end? Oh, yeah, yeah. Gaussian connections, I think they mean softmax, I think. I think softmax. I think they finally get a softmax. That's what I'm thinking, but we consider there are learnable parameters there. Yeah. Yes, yes. I think you are right. You can question whether there is a learnable parameter there, but I think from 84 to 10, you have to have connections, right? Otherwise, how do you get the 10 structure? After that, I think they are doing softmax. That's the good question. Very good question. Thank you. I didn't even notice that. Okay. Any other questions? Okay. So then when you look at the ImageNet came in 2012, then after that AlexNet came. We saw that in the morning. So AlexNet structure was like this. They had two GPUs, the top GPU and the bottom GPU. This is the original diagram in the paper also. This is the top GPU and this is the bottom GPU. So they distributed these convolution kernels between these GPUs. So the image was color, 3 channels, and 224 times 224. Maybe it is 227 by 227. Maybe there's slight change there. They ran 11 by 11 kernels to quickly reduce the size to 55 by 55. Quickly reducing the size is very important. Otherwise, it's computationally very expensive. Then they had 48 of those convolution kernels in the bottom GPU, 48 of them in the top GPU. So therefore, altogether 96 of them. Then we have they had 5 by 5 convolutions, giving rise to 27 by 27. So that means they had structure totally being reduced. Okay, max pooling also. Convolutions after that, max pooling. They had 128 of those, the top and in the bottom. And then another max pooling layer to downsample to 13 by 13, 192 in the top one, 192 in the bottom one. Then again, convolutions, 3 by 3 convolutions to generate 13 by 13, the size remains, so they must have done padding, and 192 of them. Then again, 3 by 3 convolution, 128 of them. Then densely connected to 2048, densely connected to 2048, densely connected to 1000. So similar to the linear, but max pooling instead of ReLU. Max pooling is there instead of average pooling. And they use ReLU nonlinearity. More data and bigger model, 7 hidden layers, 5 convolution layers, and 3 fully connected layers. Altogether 650,000 units, 60 million parameters. GPU implementation, 2 3GB for GTX 580 GPU cards. 50 times speed up over CPU. Trained on 2 GPUs for a week. And they had so-called dropout regularization. This is that famous paper, AlexNet paper. Okay, so we will look at a simplified version of that. So the bottom GPU, top GPU have been combined for us to easily understand. So considering 227 by and 227 images and color images, depth is 3, 11 by 11 convolutions. You can see W minus K divided by 4, stride is 4, plus 1, you get stride is 4. You get 55, so 96 kernels. So that's why this is 96, 55 by 55. And that one you do 3 by 3 max pooling. It's stride 2, because it's stride 2, you sort of get half. So 5 by 5, 25, 55 by 5 by minus 3 divided by 2. This 2 is the stride plus 1. So I hope you remember the formula. It's 27. And this number of channels or the depth remains the same due to max pooling. And then 5 by 5 convolution with pad into 256 kernels. So you can see the thing, this is propagating like that. And then finally you have a 6 times 6 times 256 structure, altogether 9,216 nodes. That is fully connected to 4,096 nodes. Again, fully connected to 4,096, finally 1,000 node softmax. Very good. If you have any questions, please ask. So now we'll do a in-depth calculation of the parameters here. Maybe we don't have time to do that, but I will show you how to do that. Okay. Okay. So these are color images. So therefore, number of channels is 3. Height and width are 227. Number of kernels is 96. You saw that on the top GPU 48, bottom GPU 48. K is 11, 11 by 11 convolution. Stride is 4. Padding is 0. What is C out? C out is already 96. There's no question about that. Then H prime, W prime, how do you get that? You use a formula, this formula, W prime equals W minus P plus 2P divided by stride plus 1. So you can see 227 minus 11 plus 2 times 0 divided by 4, you get 55. That is 55. Okay, how about the memory required for this? So what is the size of the structure? 96 times 55 by 55. So 96 times the number of elements, bytes per element divided by 1024 to convert them to kilobytes. So output structure size is 96 times 55 by 55 bytes per element. So we need the 32 bits, right, for each of them. So 4 and then 1024 to divide. So 32 to 1134 kilobytes. How many parameters? We know that there are 96 kernels, 11 by 11 of them. And of course, the biases will be there. C out times C in times K by K. So this is the size of each kernel. There are 96 of them and the bias. So 34,000, approximately 35 kilo K parameters. How many floating point operations? To compute floating point operations, we have to look at the structure of the output structure size. And for each structure, we have to run a convolution. Size each cell, we have to run a convolution. So number of floating point operations, the multiplier operations, number of output elements, that means the size of this, that is 96 times 55 by 55. And each of them we have to run the 3 times 11 by 11 convolution. This is 105 million. massive, massive floating number of floating point operations. Okay, so like that, we can keep on computing this based on the previous diagram that I showed you, and we can see the total number of the output size, memory, and all these animations I have done based on Justin Johnson's slides. Then finally, we have the structure size of the last layer to last convolution layer, 9216 is the number there. And then that is fully connected to 4096. So therefore, fully connected 6 parameters, C in times C out plus C out for the fully connected layer, or fully connected, or C in times C out. All the nodes are connected to all of them, plus the biases. So you can see 37 million of them. And then this one also can be computed like this. Floating point operations, C in times C out. So this is the number of operations. So then we can observe that here, memory is decreasing. Parameters is increasing. Total floating point operations is decreasing. So this pattern is there in any convolutional neural network. So this is the full analysis of the AlexNet. Yeah, okay. So if you ask how did they do that, they did that with trial and error. So unfortunately, later on, people came up with methods of doing that properly. So we did a brief examination of the amount of memory used. So you saw that in initial layers, the amount of memory used was very high, for example, here. And number of parameters, it becomes high due to the fully connected layers. Uh, Number of mega floating point operations, high in the early convolution layers. So you can see early convolution layers high in memory because of the image size. Parameters high due to fully connected layers. Amount of computations high in early layers due to convolutions. Convolutions are computationally expensive, but parameter wise small in number. So these are the conclusions that we can draw from AlexNet, justifiable, applicable to other similar convolutional neural networks. Okay. So then rest of the things we can look at what happened in 2013 and so on. So we will look at those things next week because we did quite a bit today. So if you have any questions, I will answer. Otherwise, you can log off. Do you have any questions about the assignment also? If you have any questions, I can answer. stop the recording. If you have any questions about the assignment and so anything, please don't hesitate to ask.